questions then. All right, off we go. So today we will do, I guess, these two problems, something called edit distance, something called matrix chain multiplication, but it's going to be, well, we'll see. Okay, so we'll start with talking about strings. So I think you've all seen this before, this kind of thing. So this is like from GitHub, and GitHub is for version control, and you save your work and you resave it and stuff. Um, but the GitHub will do things like, oh, the difference between this file and this file are these lines of code, right? So this was like some GitHub from I think the textbook or something many years ago. We pushed some deadline back, right? Okay. So how does GitHub highlight changes? Well, it's using something called diff. So diff is going to compare files like line by line, and it's going to try to figure out like the minimum number of like line by line changes that need to be made to convert one file into the next. So this can be a little tricky, right? So you have some code and you insert like a new function up at the top. So some of all the lines are like shifted down. So diff needs to recognize that, oh, this third line matches the second line here, fourth to third and stuff, and it's only the new thing that's being inserted. And if you're starting to insert and delete a lot of stuff, then there's sort of like different ways to match, right? And you want to sort of find the minimum number of changes you need to kind of give the minimum description. And people generally find this to be more useful than not. Okay, so that's called diff. So another application we'll look at is something like genetics, right? So I'm not an expert, but I guess our DNA is sort of encoded in four letters, right? A, C, G, and T, which stand for, I guess, protein. Anyway, huh? Yeah, I did my report in fifth grade on this. Deoxyribonucleic acid. I remember learning this in fifth grade. Okay. Um, right, but idea is that this somehow encodes, this is like some kind of recipe book for how your body is built. It encodes a lot of information about you, uh, so on and so forth. And there's a lot of interest in trying to understand how similar two different DNA strands are, right? And I think for context, how big is one of our chromosomes? How many letters? Peter, how big is our DNA? Yeah, is it gigabytes or terabytes? I kind of forget. Don't know? Billions? Okay, okay. So there's billions of letters you want to compare and things like this, right? Okay, so why do people want to do this? Uh, you know, you want to analyze like hereditary traits or something or diseases. Okay, some person has some symptoms, some person doesn't, but they're siblings, only a few letters are different. Maybe some letter can explain some change. Okay. Or like if you're trying to reconstruct what's called the tree of life, how animals evolve from each other, then you have some sort of like, oh, well, they come from the same species, there'll be some similarities in genetic code, things like this, right? But based on the magnitude of differences and various patterns, you could try to reconstruct the past, right? Even for extinct species, if you just have some trace of some DNA. Okay, so that's another kind of uh, large scale problem. And so I can think of at least two different ways to compare strings and get some measure of similarity. And the first one that shows up a lot in like coding theory, is called Hamming distance. So this is where you just get two strings of the same length, and you just go through and say how many of the letters are the same and how many of the letters are different. Okay, so like let's take X and Y here. Here I've taken X and I just removed D and put it back at the end. That's why they look kind of similar. But what would be the Hamming distance between these two strings? Yeah. Oh, 4, right? So these four letters are all off. So you get a Hamming distance of 4, right? And you can already see a little bit of the weakness. I really only made a relatively small change, but the distance is like more than half the letters. Okay, and so the second one, right, which might be more intuitive, is like imagine I'm at like a keyboard, okay, and I already have my string X. How many changes do I have to make to get from X to Y? Just kind of how many keys do I have to press? So you have 3 operations. I can delete a letter from X, I can insert a letter into X at any point, or I can take one letter and replace it with another. Okay, so you can insert, delete, or replacement. And how many operations are needed to convert one string into the other? Okay, so okay, in this example, you came up with 2, and what would that be? Yeah, delete the D, insert it at the end. That's 2 operations. I don't think you can do better. Yeah. Okay. So those are like 2, potentially different ways to decide if 2 strings are similar or different. And so maybe the first thing to point out is they're both metrics, mathematically speaking. Do people know what like the rules or definition of a metric is formally? So it's going to be some function like d that takes as input 2 things, and you want to output something that looks and behaves like distance. Of course, Euclidean distance would be a metric over the Euclidean space, but you want to be able to like reason in the same way over strings or various other objects, right? So if I can define something that kind of resembles our intuition for like a metric in Euclidean space, then I can still do other things, right? So if you don't know the formal definition, then what would be some good properties of a function d that takes as input 2 things? Okay, a function of 2 things and outputs some value, right? Like 10 or something. So you're trying to find a function, and what are some rules you want to endow? Yeah. Okay, so symmetry. Which one's symmetry? Can I remember? Yes. Okay, good. So our notion of distance is like distance from me to you should be the same as distance from you to me. Okay, symmetric. Yeah, non-negative. It's hard to guess. Is that this one? Yes. Okay. Awesome. So distance should be non-negative. Yeah. Okay. You shouldn't be able to go back in time. Okay. What's another one? Triangle inequality. This one I know is the last one. Okay. So if I'm trying to get from point A to point B, right? Pick any other distance, other point C. The shortest way to get from A to C, followed by C to B, that sum should be greater than going from A to B, because at some level, it is going from A to B and going to C on the way. Okay, so it should satisfy the triangle inequality. And then what's maybe one more rule? Yeah, yeah. So strictly speaking, really for a metric, 2 points should have distance 0 if and only if they're the same point. Yeah, I mean, often in geometry problems, if there's no distance, we just treat them as the same. There's some situations where you relax this, but yeah, this is a strict definition. Okay. Now, and I want to point out that both of these measures of or similarity on strings satisfy all these properties, right? Like take Hamming distance. That's just how many letters match, right? Of course, it's non-negative, and if the distance is 0, that means all letters match. They're the same. And then it's symmetric, like going from X to Y, same as going from Y to X. And then there's a triangle inequality, which I think you have to look at a little more carefully to convince yourself. I don't have a one sentence zinger. All right, now let's look at edit distance. That's when I'm like modifying one string with insertions, deletions, substitutions to go from one to the other. Yeah. So again, we're counting something that's non-negative, so that's okay. The first one's done. The second one, this one, oh, yeah, the second one, right? If 2 strings are the same, you don't have to make any changes. If you don't make any changes, 2 strings are the same. Good. Okay, the third one is maybe more subtle. So the third one says that the edit distance from string A to string B should be this edit distance from string B to string A. Why? Yeah, and what would that reversal look like? Yeah, so insertions will become deletions, deletions will come in insertions, and substitutions will, I think, essentially remain the same, but I think they'll reverse the role of the two. Yeah, so it's actually a symmetric thing. And then triangle inequality is actually not so bad, but who can argue that the triangle inequality holds? So it's saying that the edit distance from string A to string B is at most the edit distance from string A to string C plus the edit distance from string C to string B. Yeah. There's a yeah. I think you're on the right. Yeah. Yeah. So that is true in that precise case, but I want to be able to sort of really say, oh, generally, right? So yeah. Yeah. So edit distance by definition is the minimum number of these operations to get you from one to another, right? And so let's say I take the operations that go from X to Y and the operations from Y to Z. I can concatenate them. Insert, delete here first, and then insert, delete, substitute next. That's some sequence of operations that goes from X ultimately to Z, uh, X to Y, even though it goes via Z, right? And the definition of distance from X to Z is the minimum number of operations needed. And this is some number of operations needed when you're going through Z in the middle. Because it's really just coming from the definition of minimum. It's doing all the work for you. Okay, cool. So, all right. So, how would I compare and contrast these two different things? Well, if I look at Hamming distance, then, I think from a modeling standpoint, what's sort of unintuitive to me is that a small misalignment can lead to a huge Hamming distance. Right? There's other issues like it only works at its exact same length. That would never work for source code. And I don't even think it works for genetics because like weird little DNA gets killed off by photons or something. But really conceptually, I think the fact that if you remove one thing, everything gets misaligned. That's not really what I think of as similar and dissimilar strings. But the pro is that it's very efficient. Yeah, it's very easy to just line up the two strings. Say, that's the same. That's not the same. That's the same. That's not the same. Right? It's very easy to calculate the Hamming distance. So I would say that would be good. And then I would say edit distance is sort of flipped in the sense that from a modeling perspective, it's more intuitive to me, especially if I'm like thinking about code because you're literally editing the code and you make some changes and that's how you want to think about it, right? So So for example, a small misalignment will only give you a very small edit distance. It's one insertion, one deletion, or something to fix it. Um, good. But then the downside is that it's clearly more complicated, and it's some optimization problem. What's the minimum number of edits needed to go from one string to another? That doesn't at all seem very easy to do. Okay. So that's sort of what we're facing. And and our goal then is going to try to figure out how to do edit distance fairly efficiently. So at some level, we can get the best of both worlds. We can get a good model, but also a tractable model. Okay? I mean, mathematically, it's tractable. It's well defined, but computationally, it's not so clear. Okay, good. So we're going to do a recursive algorithm. And at first pass, we're just going to try to do a straightforward recursive algorithm. Okay. So as usual, I'm going to force you to come up with some sentence defining what we want to accomplish. Okay, so first give it a name. Oh, diff, okay. And maybe we can make clear our parameters. Yeah, and okay, so I'm going to phrase that as minimum number of edits. It's like good to make explicit like the type of your solution output, right? Minimum number of edits uh, to convert X to Y or something like this, right? Nothing special. I think that's basically what I had typed up. Okay, so given two strings X and Y, we want to write an algorithm that computes the minimum number of edits to get from X to Y. Okay, I'm just restating sort of what we've already done. Okay, let's implement this. Yeah, so let's try to implement this. So you're going to try to implement edit from X. It's supposed to be an M to Y. Okay, so let's try to implement a recursive algorithm. Yeah, okay. So you said out loud, if M equals 0 or N equals 0, return M or N. Uh, and I guess as a tricky shorthand, I think you can write return M plus N, and that'll do the work for you, just to avoid writing too much. Not that usually when you're coding, just make it easy for me to read, but here I'm lazy. Okay, so good. That's a fine base case, right? If either string is empty, if if uh, if X is empty, then you just kind of delete a bunch of things from Y. If Y is empty, you're going to insert everything from X. I don't see how you could do better. Fine. Okay, so the interesting case is when they're both non-empty. Yeah. And what? Okay. If X is equal to Y, return 0. Sounds okay. I do want to point out that this will take M plus N time to do, even though it looks like one line of code. Min M, or it's, oh, yeah, I guess min's a little different than max. Okay, sure. M plus N is an upper bound. Okay, fine. So those are easy cases. Yeah. Okay. How am I going to write that down? So first, whenever some student starts an answer with just, that's always a sign of trouble, but still. Okay, so I want to somehow articulate, iterate over all something something. So let's make that precise. Okay, so let x prime delete ith character from x, and then return 1 plus edit x prime y. Oh, okay. Uh, A is equal to 1 plus edit. Okay. And then I guess you want to do something similar for, okay, so, okay, so how do I do this compactly? Uh, okay, so you also kind of want to try 1 to n, let, I guess x, okay, j is equal to, oh, 1 to m, this should have been m, 1 to n, let X prime insert Yj into the ith slot or something, which I guess maybe we should write m plus 1 because it could go at the end or something. And then b is like 1 plus editing these two things. Okay. And then presumably you want to do something similar for substitute. Okay, so I is going to go to 1 to m, j is going to go from 1 to n, and then you're going to do some kind of substitute xi with yj and recurse or something on the two new strings. Yeah, so let me take a step back. So, okay, so first of all, my handwriting's not great, as you all know, but is the idea clear? At some level, we're kind of doing some form of try everything. I'm going to try all the possible insertions and recurse on all of them. I'm going to try all the possible deletions and recurse on all of them. And I'm going to try all the substitutions and kind of recurse on the change strings. And I want to, which sounds pretty conservative, right? If you're trying everything, nothing can go wrong. But there's one, or at least one issue. Yeah. Okay, so we'll do that in a moment. But like, I first want to note that there's like, let's say you're trying to prove this thing works, right? Because at some level, I could say, oh, you're going to try everything, so it's going to be fine, right? What could you possibly miss? But imagine, for example, I try to do a proof by induction. Oh, and yeah, at the end, you return a minimum of the three things. Sorry, I didn't write that out. Yeah, try everything and return the best one. But I would say even formally, there's an issue if you're, say, trying to prove something by induction. Yeah. Yeah, that's absolutely true. But I want to pinpoint it more. Let's say you tried to prove something by induction, right? And you have your inductive hypothesis, and you try to apply it. So what goes wrong, right? There must be an issue because exactly what you said could happen. Yeah, our problem size isn't going down. Yeah, so that's going to create some problems. In particular, inserting back in is sort of an issue, right? So our problem size actually isn't even going down. So in some sense, we didn't even quite come up with a proper, recursive algorithm that even is applying induction. Yeah, so it's non-trivial. Okay, so let me create some space and try again. We'll keep the base cases. Okay, something like this. All right, so what was another approach then? Yeah. Okay, so this might be what you actually do yourself, right? So, right, it's going this way. So you look at the first two letters and say if they match, then I should just figure out how to convert the rest to each other. Okay. And here we're clearly making some progress, right? Both of the arrays are getting smaller. Else, right? So that means that the first letters are not equal. Now what? So you're looking at two strings, the first two letters are not the same. Yeah, so you're gonna have to do something to get the first letters to work, right? And what should you do? Okay, so what are the three cases? Sorry, dude. Uh-huh. Okay, so the two letters aren't the same. I'm going to do something. And my three choices are to substitute. I can just directly relabel this letter to that letter. Or I could insert, I guess, the first letter into Y. Or I can delete the first letter and then worry about the rest. Okay? And often when I ask that question, I often get solutions of the form, well, maybe depending on the second letter, you can decide whether to do an insertion or deletion or substitution, right? Maybe substitution's like, oh, isn't that always better? But no, maybe the next letters could have matched or something. You're better off deleting, something like this, right? Maybe you can try to look down the sequence and try to figure out what you should do, right? And that's always very tempting, right? Like, oh, what should I do? Should I insert, delete, or substitute? Let me analyze the rest of the string, see if I can come up with something clever, okay? But we are not going to do that. That's very hard to do. I mean, you'll be tempted, but it's very hard to find something that actually works. So what you can do is you can try all of them. So on one case, I can try substituting. So if I substitute, that's one operation, um, and then I have to edit the rest. Okay, I can try inserting, which I think just will remove the first letter from X if I did that correctly. So I'm going to insert from X into Y. So then that's one operation, plus I have to edit the rest of X into all of Y. Or I'm going to delete the first character from Y, and then I have to edit all of X into the rest of Y. Yeah, I know I have to do one of those three things just to get the first letters to match. And I don't know which, so I'm going to try all three and take the min. Yeah, and that's very conservative. Any edited solution has to do one of the three, otherwise the first letters won't match. You're just going to try to guess. Yeah, so you don't need the base case. Yeah, so you don't need this. And actually, I think you'll find when we look at the end that this would actually make your algorithm slower because it takes a while to scan the whole thing. Okay, so this algorithm is like so conservative, trying everything basically, that yeah, you don't have to worry too much about it. Okay, so you can nick it. Fine. So okay, that's what I wrote here. I want to make one minor point here. It is true, if you think carefully, that if the first letters match, you should be able to just match them and keep going. But to prove it's correct, you'd have to write like a paragraph saying, oh, it seems obvious, but to like write it out, carefully takes a little bit of thought. So as computer scientists, you could be extremely lazy and say, even if they do match, I'm going to try all three anyway. I'm going to insert and delete just in case. Yeah, be very conservative. So that's why I did in the pseudocode here. It is true that if you scrutinize it, you don't have to do those two steps. Okay. Um, Good. That seems a little bit silly for this problem, but there'll be other problems maybe that are more involved and a more complicated story, and you're sitting around worrying about this, and you can just say, screw it. If it doesn't hurt my running time, I'm okay with it. Okay. So, all right, this algorithm is correct, but what's the running time? How do I model it and stuff? 3 times tn minus 1 plus like some constant amount of work. Yeah, so then you're going to get 9 times tn over minus 2 plus 3. Oh, okay, yeah, you can do a little bit better. So I'm just going to be a little bit lazy here. Okay, so it'll be at most 3 to the n, and that means it's also at least 2 to the n because you're at least going to get at least 3 calls where you, oh, yeah, or 3, it's at least 3 to the n over 2 or something, because maybe you subtract 2 at a time. Okay. Uh, right, but you're definitely looking at something that's exponential, maybe 3 to the n over 2, I don't care too much. Okay, so It's a working algorithm. It's a correct algorithm. It's a relatively simple algorithm to write out. It's clearly correct, but it's slow. Okay, so that's where things currently stand. Clean algorithm, everything is great. The only issue is running time. Okay, so the real more general question that we're interested in is, keep doing that. How do you make a recursive algorithm fast? So recursion is great. With the power of induction, we can get a correct algorithm and feel very good about the correctness, right? It's just taking a baby step. It's not a complicated proof of correctness. So that's fantastic, right? From the basis of homework 0, we did a perfect job. But the only issue is running time. So how do we make this algorithm faster? Any ideas? Yeah. Yeah, so what we're going to do, so at some level, if you look at the code and you imagine it working on strings, you might notice that it's going to do a lot of redundant work, right? Like think of like the same substrings can appear from many different paths, right? Delete the first one, delete the second one, delete the third, or I can delete top, down, top, down, top, down, right? There's many ways to get to the same subproblem. And the same subproblem should have the same solution, but there's many paths to get there, right? And that's where you're getting your exponential running time. So what we're going to do, we're just going to cache our answers and see how much that wins us. Okay? So a very simple idea and kind of a very computer sciencey idea. It's not a mathematical idea, right? It's only interesting for computers. Okay? All we're going to do is take our clearly correct recursive algorithm and make sure that we save our answers to every subproblem we solve. Oh, okay, this is the edit distance from the last 10 characters to the last 15 characters. I solved it once and I'm going to write it down. I use a hash table, I use an array. I'm just going to write it down. Okay? And if I come across that subproblem again, I'm going to make sure to look up my table to see if it's already there. Okay? So that's all we're going to do. So let's work in slightly. So to make everything a little more cache friendly, I'm first going to rewrite some of the stuff we did to kind of focus on the indices. Okay, so instead of like always having an array index from 1, let's say, okay, suppose I have kind of globally fixed 2 arrays, x1 to m and y1 to n. You need some frame of reference. And I'll define edit I comma j to be the edit distance from xi to m and yj to n. Ith character on, jth character on. So same thing as before, just re-indexing. Because I want to make it like very easy to save my answers. Okay. And then we'll just re-implement the algorithm we just did, but just in terms of ij, right? Not always passing x and y around. Okay, so we can go through it slowly. But, you know, oh, there's a typo, of course. If xi is not equal to yj, then I'll try each of the operations. Try substituting and I increase I and j because I've taken 1 off each array. I try inserting, I only increase I. I try deleting, I only increase j. I might have got that backwards, but okay. Exact same algorithm as before, it's just in terms of ij instead of xy. Okay. Good. So that hasn't changed. Now we can take this code and what are we going to do? So I have m times n subproblems, right? From all the different substrings. And so that's m times n different answers. So just like allocate a big array, 2-dimensional array, m rows, n columns or something, or you can just use a hash table, right? It's not hard to save things anymore. Yeah. Okay. And let me zoom in so it's easier to see. I don't know if you can see otherwise. Okay, so I've highlighted the only differences. Okay, so after the base cases, you don't need to save answers for base cases. They don't take any time anyway. Now, instead of immediately trying insertion, deletion, or whatever, I'm going to check my table to see if I've already put an answer there. So I check to see, oh, if that entry aij is null, that's like to indicate nothing is there. Yeah. And if there's nothing, then we'll do exactly what we did before, but we'll save it. I'll set aij to be the answer of our recursive computation, and for either case. Okay, and then I'll return whatever is the saved answer. Okay, so this is conceptually the exact same, like logically it's the exact same algorithm. And we're just doing this common sense thing of like, oh, let's not do the same thing twice. If I solve something, just write it down. Okay, good. So we do that. And why is this there? Okay, good. Okay, so the only difference is that I'm saving my answers, right? And now let's try to think about the running time of this algorithm. Okay. So every subproblem you only genuinely solve once, right? And other times you just find in a table, you return it in constant time. So that recursive call to a solved problem is just some constant time thing. Okay. So to account for all the work over this recursive algorithm, it suffices to say, how many subproblems are there? And how much time am I spending on each subproblem, excluding the recursive calls? Because that's accounted for in a different subproblem. And just add it all up. And that would give me the running time of the entire algorithm. So in this case, how many subproblems are there? Mn, right? So that's how many choices of I and j are there. And how long does each subproblem take to solve? Constant time, right? Because you just like make 3 recursive subcalls, you compare 3 things, no big deal. It takes constant time. Okay. Multiply that together, and what's your running time? Mn. Okay. So now you actually have a pretty efficient algorithm. So yeah, maybe I'll sit here for a moment. So this is quite nice, right? It's a very general approach to algorithm. I take some problem, it seems complicated. Okay, I can make a conservative recursive algorithm, and it's clear by induction that it'll be correct. Right? Correctness was not so controversial with that initial algorithm because it's so clean and simple. And then I made it efficient with this little trick, right? This trick that everyone would do in practice anyway. Right? Like, why are all web servers fast? Because they cache everything. Why is Google fast? Someone else already asked that question, right? Caching is already a standard thing. So right. So that's it, right? It's a very powerful technique. So this has a fancier name for no good reason, like literally no good reason. It's sometimes called dynamic programming, which I understand the guy who kind of came up with this idea, which I think was Fulkerson, at some level wanted to impress his boss. Okay? And so what you're saying is like, okay, if your recursive algorithm has a limited number of subproblems, then you should save your answers. If it's exponentially many subproblems, okay, that's the world of hurt because you'll need exponential space to write everything down. You won't save any time. But if you have this recursive kind of top-down understanding that breaks it down to a modest number of subproblems, in particular a polynomial number of subproblems, then you can start saving your answers and immediately getting a polynomial time algorithm. Okay, so compared to before, you need to break things down in a somewhat efficient way, a compact way. Okay, but then you're done. Okay, so in our class, I have somewhat strict rules about like steps you need to follow for one of these solutions just to make sure you go through certain motions. Okay, so I'll go through them. Hopefully they're not too onerous. Okay, so um, okay, 6 looks like a lot, but you already did all 6. So the first one you always have to do, right? Figure out the recursive spec. Figure out what the subproblems are, what the parameters are. Okay, for most dynamic programming problems, this is like 99% of the battle. You figure this out and you take your time and you had a mild amount of sleep last night, you'll be okay. Okay, so step two is uh is implement the thing. Okay, implement it recursively, and don't worry about the caching. Just worry about getting it correct. Don't worry about it being fast. Write that first recursive algorithm we did, which was pretty easy to read, and we could all kind of pretty easily agree that it's correct. Okay. I think the third step we forgot to do. Third step. So rather than having, okay, so every time we have one of these problems, you write a recursive algorithm, and then you're like, okay, now I can make a table, save my answers in a table. You rewrite the whole thing, with an extra if-else statement around it, right? That's obviously a waste of everyone's time. Okay. So in this class, you just say, I'm going to take my recursive algorithm and I'm going to apply dynamic programming, or I'm going to apply caching. That's enough. Just write the word dynamic programming, and we understand you're going to do the exact same thing every single time. You take your code, you wrap it in a table, right? There's no creativity involved. So no bother. It just makes it harder to read, right? Because it doesn't tell you anything about correctness. So you just have to mention that you're doing dynamic programming, analyze the running time. Usually it's just adding up over all the subproblems how much work there is to do. Sometimes there's moments for cleverness. Sometimes you'll find, oh, you could do some binary search in the middle and it could be a little bit faster, or this or that. Some moments of cleverness will be here and there. But by and large, it's not too complicated to analyze the running time of these algorithms. Okay. 5, we didn't do this explicitly. So once I define like our code up here, right, which is defined in terms of edit ij, okay, but we had some original problem, right? I want to get the edit distance from x between the whole string to the whole string. So you just need to write some sentence like for the original problem. You don't have to write, you're going to return x1, edit 1, in this case, right? That's what you're actually looking for. We were involved in the subproblems. That's obviously the meat of the thinking. But at the end of the day, you want to return edit 1. So somewhere in there, you just have to say, I'm going to return edit 1. For this problem, it doesn't seem that interesting. For other problems, it can actually matter. Okay. That's another step. And then the last step is some kind of proof by induction. And this should be usually pretty straightforward, assuming you have the right recursive spec, right? Because that'll be your inductive hypothesis. Oh, okay, the optimal solution must do this or this. If this, then that. Yeah. Okay. And often on homework, we'll do things like rather than having you do all the proofs, I'd rather give you like 5 subproblems and you can skip the proofs, things like this. But okay, but a complete solution would require some kind of proof by induction. Usually straightforward. Okay, and those are the only steps we're going to look for. Okay. Um, Good. So maybe I should make explicit what we don't want, because if you look up our homework solutions on like Geeks for Geeks, you'll give me all the things we don't want, and it's a big mess. Okay, plus the fact that you're cheating. Okay. Um, okay, things we don't want. The code implementing the caching, again, I don't care. Right? That's mechanical, and it just obscures the ideas. 2, uh, the iterative code with loops. It is true, like with edit distance, right? You're filling out this table. And it's much easier to think about recursively, but you could reverse engineer how to like build it from the last corner back up, right? And try to do 2 loops. I don't want that ever, right? That again just obscures ideas like who cares? It is true in practice, it might be a little bit faster, but I don't care. I only care about correctness, right? And trying to get more and more complicated things that we can do with dynamic programming. So we never ever want to see this looping code. Yeah, it just makes it hard to read. Okay. And then the last thing, we're not going to worry too much about space usage. It's almost always the number of subproblems. There are a few tricky problems where you can like, there are some problems where like imagine the table. To get one row, you only need the row right below. So you can, in principle, like only, use less space. Okay, this clearly doesn't matter, right? Okay, it's kind of cute, it's kind of clever, but it doesn't matter. I'm really much more interested in kind of top-down correctness, and I'd rather push, and see how complicated of a problem we can handle than to worry about these low-order things. Yeah, if you can do the big things, with care, you can do the little things. Okay, good. All right, any questions? All right. Then, oh, here's some sample solution. It's about as boring as it looks. Yeah, doesn't matter. Okay. But there's some sample solutions in the book that you can like follow. All right. But any questions about edit distance? Otherwise, we'll do another application. And if we have time, we'll do some extra problems. Okay, good. All right, so our next application is going to come from multiplying matrices. Okay, so just to refresh, right? So let's say I'm multiplying two matrices A and B. Okay, so when I multiply two matrices A and B, I'm going to go across A and down B. So that means the number of columns in A needs to match the number of rows in B. I also often think of that as like the inner dimensions, right? If it's like n1 by n2 times n3 by n4, the inner dimensions n2 and n3 need to be equal. I always think of it like zipping it together. Okay, so each entry in C, the entry 5 comma 7 is going to go through the fifth row in A and the seventh column in B and just zip them together. Take the dot product, multiply numbers, and add them up. Let's go do that for every entry. Okay. So what's the overall running time to compute C if the dimensions are n1, n2, and n3? The inner dimensions n2. Yeah. n1, n2, n3. Yeah, so there's n1 by n3 entries in C, and each time you're zipping through this list of n2 numbers. Okay. All right, so this you're probably well aware of. So you implement this with loops. Okay. Now, when you encounter a situation like this, you're multiplying three matrices, you actually have some choices to make, right? So multiplication is associative, so I can choose which two to multiply at a time. Yeah. And that can actually make a big difference on the running time. So, okay. So I can either multiply the first two first and then the third, or the last two first and then the first. Okay. So if you did the first approach, okay, your intermediate matrix will look like this. So multiplying those first two together will get you a big square matrix. Okay, and then you multiply the last one, the final one will always have the same shape, like this. Okay, so how long would this take? Maybe it's awkward to say. Yeah. Is that what okay, so the first multiplication will take n1, n2, n3. Uh, yeah, just multiplying these axes together. Uh, right, which I guess you can group the terms. Um, okay. And then the other one is going to give you a different character. So if you do the last two first, then you're going to get a very small matrix from that product. You multiply those together, and your overall running time is going to look something like this. Okay? And, okay, so what's the point? So in this picture, N2 and N4 are small, and N1 and N3 are big. Okay? So in the first one, you're getting N1 times N3 times the two small ones put together. So you're really paying the big one squared times small one. And in the second one, you're getting small times the two big ones put together. So you're really getting small squared times big. Okay? So the second one, you get to trade off a big one for a small one. So this will be better. Okay? So how you choose your operations can matter. Okay, so in general, you're going to be given a bunch of matrices and assume that the dimensions like kind of match. Okay. And you want to figure out the best way to do pairwise multiplication to get the final output and just minimize the number of operations, right? All these n1, n2, n3s added up. Okay, so, right. So for the input, it suffices to just give you the dimensions n1, n2, n3, n4, n5, where, n1 or n2 is the last dimension of the first matrix and the first dimension of the second matrix, and so forth. Okay, all right. That makes sense? Okay. So, right. Okay, so any ideas? You just want to make a recursive algorithm or worry about running time afterwards? Yeah. Okay, so if I understood you correctly, I want to compare this possibility, something like this, with this possibility. Yes, yes. So at some level, you're saying I either multiply the first with the second, and then the rest will be taken care of and then multiply together. Or I don't multiply the first with the second until the second and everyone else has been merged together. Does that make sense? Is that comprehensive? Yeah. Well, okay, so you can only you can't like permute the matrices because that would change the output. Plus the dimensions might not match. Sorry? Well, I'm hinting it might not, but so is there like a greedy strategy where it's like, well, if I want the intermediate matrices to be small, so I just find the smallest matrix and try to deal with its neighbors or something? Yeah, I mean this is not the perfect picture, but but some level still some kind of like aggressive, kind of greedy, or some kind of like, can I analyze the situation, pick out which ones to multiply? Okay. So yeah, so can you do some kind of strategy, real strategy? So that yeah, so I think one thing that gets a little bit tricky is what looks appealing in the short term. It's not clear that it's going to be the right thing because things kind of evolve, right? There's like this path dependence. So it's not clear that what seems to be appealing, like, oh, let's get this small matrix right away, is really what you want overall. Maybe you want to save this matrix to make something else smaller later, if that makes sense. So it's tricky, yeah? Well, yeah. Well, first, let's go back to this, like, the first strategy, either merge the first two or basically don't. And was that comprehensive? But what would be an exception? Yeah. Yeah, so maybe that's what you mean. So even if you did this first too, right? Maybe you would still want to multiply like that afterwards, which if you had grouped these together, that would eliminate that possibility. So even if you decide to do these two, it's not clear what you want to do after. Oh, sorry? Yeah. Yeah, so maybe here's a different perspective. So at the end of the day, you're going to do some kind of parenthesizing solution. Okay, so it's always going to have some form like this, which you can imagine as, hello, as a tree, right? You take the last two kind of outer parentheses, and that's going to break down into these subproblems, right? So from this perspective, it's a little bit easier now to maybe figure out what decision to make at a time, which at some level is try to figure out the root of this kind of parse tree. Try to figure out the first outermost split, which could be anywhere along the thing, right? So you're trying to figure out from a matrix multiplication standpoint, that's the last two things you're going to multiply together. It's going to be the first decision you make from a top-down perspective. Okay, so that's what we're going to then try as an approach. Try to figure out how to split this thing uh, in half or into two parts, not equal halves. That'll be our outermost grouping. Okay, so that will be oh, okay, now so those are the ideas. Okay, good. So now let's try to figure out how to implement this thing and then see how we do. Yeah, great. Yeah. I don't know why I chose fastest, but yeah. So I'm just gonna, so the key thing, okay, so let me read it out loud. The minimum number of operations to compute the matrix product AI to AJ. And I think the most important part of that is the AI to AJ, because in that you have defined the subproblem. My subproblems look like subsequences, which in particular, the starting point and the end point are both variables, right? When I was doing edit distance, my subproblems were defined by suffixes, right? And that's a certain kind of structure that defines the problem, defines the algorithm. By the time you kind of figure that out, the rest follows relatively quickly. Here too, you want you to figure out what the subproblem is, and we'll do it in a moment. Things are going to fall together much faster, right? But I think the key thing is to recognize, oh, the subproblems look like these contiguous subsequences. Hopefully, or maybe that will register more in hindsight. So, okay, let's implement this then. So, fastest ij. Yeah. Oh, if I equal j, I think if I equals j, then you're just multiplying AI with nothing else. At least the way the sentence is defined, so you just return zero or something. If I is bigger than j, you can return zero, return infinity. Actually, maybe you should leave it blank. Well, I'll put infinity because that's what suggested, right? Okay, so interesting case is if I is less than j. Yeah, okay. If j equals I plus 1, return, how did we do the input? Uh, I think it's going to be ni plus 1, ni plus 2, which for those keeping score, that's j and that's j plus 1. Okay, I think that's how we uh, define the input. Okay, good. Okay, but the interesting case is when I is less than j. Yeah, okay, so iterate. So I sometimes use this notation, which isn't really proper code, because it's a loop, in there, so you just have to remember that. But it's easier to see the ideas. So, okay, so what should I write here? Yeah. So even after you split into two groups and figure it out, you have to put it together at the end. So Ni, Nk, Nj plus, yeah, I think it's k plus 1. Let me put it below because I'm running out of space. Ni, Nj plus 1. Dang it. No, it's Nk because it's from I to k minus 1. Yeah. Just take our time, we'll get it right. Off by 1. It's a natural thing. Okay. How does that look? It's a small bug, but it's mostly correct. But okay, the code is looping over all k from I to j, take the minimum over all possible choices, yeah? Yeah, so you want to be a little bit careful here, otherwise your algorithm might not terminate. So I plus 1 up to j minus 1. Okay, so you just have to be a little bit careful. Whatever you write down, just double check your fence post at the end, just like the binary search problems and stuff. Yeah. If Yeah, so is that strictly necessary? So yeah, if we had just done k equals I plus 1 to j, it would have, I think the code would survive even when k is equal to j because it would return the base case correctly. In fact, I think for correctness, you need to consider that option because maybe you want to group all but the last one, have the last one by itself. Okay, so, huh? What's n? Oh, these are dimensions of the matrix. Also, k might have been a bad choice because there's k matrices in the input. Uh, okay, so we'll make this h. Okay. You can always go Greek. Yeah, that's true. It makes us feel smarter. Okay. Does that code make sense? Yeah. So even we hit the high level ideas, it's good being just a little bit careful on your indices, on your base cases and stuff. Obviously, it's still mostly correct and will just take us off a small amount of points just to piss you off. Yeah. Okay. All right. Okay. But otherwise, that's an algorithm. Okay. Um, yeah. So I guess this was my version. Okay. Obviously, I'm playing some kind of like textbook golf where I'm just trying to write something short. Um, okay. Uh, yeah, but this is fine. Okay, good. So much for that. All right. Now we have a nice clean recursive algorithm, but there was some original problem we wanted to solve. Okay. So how do I actually use my recursive algorithm to solve the original problem? I made the same K mistake. Yeah. Yeah. Okay. You're going to return fastest 1 to K. This should have been an H, H, H. I'm pretty sure I have the exact same typos every year and I forget and anyway. Okay. Yeah. The input was K. It's in this corner. There's K matrices in the input. There's K plus 1 indices for K matrices because of the inner outer or first and second. Yeah. Okay. All right. So that's another step. Okay. They say, okay, I'm going to use dynamic programming. No need to rewrite anything. And then if I'm going to use dynamic programming, what is my running time? Yeah. Yeah, so work with me for fun. There's k-squared subproblems. Okay. And how much time do I spend on every subproblem? K, because there's actually a loop in there. It's a loop of size j minus I, but actually you're going to get most of them are going to be of length close to k anyway. So rounding up is not going to hurt you. You actually need k time per subproblem. Okay, so here we actually have a loop in our code. So that will happen sometimes, so you just got to be a little more careful. And then you multiply that all together and you get k cubed. All right, so good, good, good. Okay, so that's the algorithm. It's a k cubed time algorithm where k is the number of input matrices and you get the minimum number of operations. Okay, so imagine you're writing like a CUDA compiler. This might actually be useful. Oh, I mean, I think I could make a painful word problem where we do higher and higher dimensional tensors, but it's going to be the same principles. Yeah, maybe that's a good idea. I think Searle would like that one. Yeah. Oh, yeah. So what are the k-squared subproblems? Or what are the subproblems? Oh, how do we define our subproblems? What was our recursive spec? From? Ah, that wasn't our recursive spec. So our recursive spec is the minimum number of operations to compute the matrix product AI to AJ. So that's where we defined our subproblem. So I and J characterize a subproblem. And how many choices of I and J are there? K for each. Yeah, technically k squared over 2-ish, but what's that between friends? Oh, we're friends or oh, that works. Okay. All right. Um, so how's that? Is that okay? Yeah, so this is like pretty useful stuff. All right, we have less than 5 minutes left. Um, do we want to try one ourselves? Okay, so I think this will end up being on your homework anyway. Maybe we'll omit the first one or something, or we just have an easy one. Okay, so here's like a sequence of like fairly kind of straight, standard type of problems. We'll just focus on the first one. Okay, so the input's going to be an array of numbers. Okay, and you know, you have a bunch of numbers, and you want to find a subsequence that's increasing. Okay, so like I can go 1, 3, 6, 9, and that's a subsequence of 4. Okay, so you want to get the length of the longest subsequence in A. Okay, you want to give that a shot? Oh yeah, you might have kind of done this before. Ah, perfect. Okay, good, good, good. So then do you remember the answer? So what was your recursive spec? I don't see a recursive spec here. Yeah. All right. LIS, acronyms are a good friend. Longest increasing subsequence. It takes as input an array. Yeah. Okay. Okay, that's the easier part. Sure. Uh, I can have a parameter I and j. Okay. A is fixed. A is fixed. If you had to define it in terms of A, it would not be hard afterwards to figure out how to make it in terms of I, of course. Yeah, so luckily this was on the homework of the LIS of AI to N, starting with AI. Okay, and I guess we don't have quite time to flesh this out, but most people, if they hadn't done our homework zero, would not include the clause starting with AI. And then you're going to find it much harder to implement this problem. Okay, but if you do start with AI, it's not so bad to implement. Um, okay, so if I wanted to implement LIS of I, all right, what should I write? Once we do this, then you're free to leave. Actually, you can always leave. But yeah, let's implement this. So what should I write? Well, AI, we're now going from I to N. So one is the beginning. So when I equals one, that's the whole array. I equals N. Okay. Okay, I'm gonna just add one more base case. Sometimes I just like to be safe. If I is bigger than N, I'm gonna return zero. It's safe and maybe that'll be useful. Sorry. Oh, so we're not doing this question. Oh, that's what you mean by, okay, I can do something about this. Uh, okay, good. All right, we have the technology. Okay, so, okay, so now the interesting part. I is less like I is one or something, right? You're looking at a long array. For I through N, first of all, did you want to use a different variable? Because I is already used. Okay. Uh, sorry, 1 plus J plus 1. I guess is less than AJ or something that needs to be encoded. Okay. Uh, so what this code will literally do is we'll look for the first number that's bigger than I and just return it. Yeah. Well, we've committed to this sentence. There are more than one ways to do this one. Let's stick to this sentence given that we're already out of time. Yeah. So you may not want to take the first number that's bigger, right? Because it may be much bigger. So you're going to return some kind of min of everything bigger. I think this should also start at j I plus 1. All of like lisj plus 1 if aj is bigger than ai. It should be max, and you should have some option of 1 if everything is smaller or something, right? If there are no choices of j. Okay, I know everyone's packing and being very polite about it. Very quickly, what's the running time? Particular, how many subproblems? There's n of them, and how much time per subproblem? and put that together, you get n squared. Yeah? Okay, but the real thing is to figure out the right first sentence, which is starting with your thing, so you have enough memory to know that this needs to be bigger than the first one. You'll find if you didn't have that explicitly or some substitute, it would have been much harder. Okay, yeah. Sorry? Yeah, that's fine. Anything else? All right, you're free to go. I guess Peter's doing office hours, so he's still here.